Hello everybody, welcome to Blue Marble Science. The globe drop formula is wrong, or at least right the hand says so. Warning, severe facial and monitor damage alert is in effect. Get out those oven mitts, push the monitors back out of punching range, and let's light a dumpster fire and have some fun. You ready, Gladys? Well, let's get to it. The other day I watched a video from a guy that calls himself Right the Hand, and he claims that this thing we call drop in our curvature calculators is just wrong, and he can prove that mathematically. Now, for those of you that aren't familiar with what drop is that blue line you see on this sketch. And drop is defined as the distance from a point, like point B, perpendicular to a tangent line, like that red line, that's tangent to another point on the Earth's surface, like point A over there. And there's a very simple formula that we can use to estimate how much that drop should be. And that formula simply says drop is approximately equal to 8 inches per mile squared. So in other words, if the distance between point A and point B is 1 mile, 1 squared is 1, of course, times 8 is 8 inches. But if the distance between A and B were 2 miles, then 2 squared is 4 times 8 is 32 inches of drop, and so forth. So let's see what Right the Hand thinks is wrong with this.
Right here we're going to start with, I guess we'll start, it's kind of math. This one's the one that the proof that can be written out mathematically to show that all your drop is just visual and it's not actual, because it doesn't add up. This is kind of the same, so this one's a little simpler. Shadow Bevet, his Penrose drop gets people to think, all right, so you start here and you're going to go. Now, when you get here, this is a mile. You will have dropped 0.67, right? That's your drop. Now, if you sight yourself back to where you were, right? Back to that dot, and then go to it, you'll drop again, because it's always drop, right? So then now you drop down another 0.6. So you sight back to where your original, that other spot, then you go back over there, you'll drop again, right? Then you look back, and you'll drop again, right? And then you'll look, and you'll drop again. Now, that what we just showed, that's not a ball.
Wait a minute. What are you doing? It doesn't work like that. If our boy Cletus is over here at point A, his tangent is this red line that he's standing on right there. And the drop to point B is that blue line way over there. But if Cletus's other brother Cletus is standing at point B, his tangent is not down below the earth someplace. It's tangent to the surface he's standing on. It's this red line. And his drop is this drop over here at A. This does not work the way you're showing it.
Okay, that's like stairs. So that alone shows me that you're not seeing a physical drop, right? Because if it was physical, when you went this way and looked back, you would see physically up.
Yeah, you do see physically up, just like I showed you.
Right? Because if you're here and you're going around and you're going down, if you go down and you do the opposite, you go back up. That's how physical structures work. You can't just keep going down, right? How would you keep going down? If you kept going down, it would look like this.
Well, no shit.
No shit.
That's a slant, right? That's not a ball. That's not, okay, so that's the first problem right there. That's the logical problem. Now here comes your mathematical problem, which and this is why it's a mathematical problem, because you try to apply mathematics to something that changes visually. Now, what are you talking about? Okay, first incremental cannot add up to exponential.
Incremental cannot add up to exponential. Let me savor that thought for a moment. Okay.
Okay, so if you have 1, 1, 1, 1, 1 can never add up to 1, 2, 4. You know what I mean? You can't do that. Now, why is that a problem for this math here? Okay, so mathematically,
x is a 1 mile section of the 5, 0.67. Mathematically, because these are we're not modeling this physically. This is a mathematical model. So all of this, we're doing mathematical numbers, okay? So you're dropping 1 mile, if it's a physical drop, right? You could say, well, it's exponential. Yeah, well, you'll pick it up. If from your original spot, if you measured in mile increments, right? This is their math. This is what they'll tell you. You'll drop down 6, 7, 6, 7, 6, 7, 6, 7, 6, 7, okay?
Oh, please tell me you're not just going to add 8 inches every time you go a mile. Please tell me you're not doing that.
So that's 5 times 0.67 for your 5 mile. If you take 1 mile incremental measurements, and this is our data. We're plotting our data. Okay, so this is what the data is going to look like. We went straight forward 5 miles. So you're going to get drop 1 mile, drop 1 mile, drop 1 mile, drop 1 mile, drop 1 mile. Now that's your measurements. We're data. This is our data. Okay. Now if you cite from 1 mile straight to 5 miles, okay, you'll get 5 times the amount of drop. Okay, so you actually, yeah. So this one added like a little over 3, right, in that area, and this one's 16. So mathematically, right, when you turn this into a math equation, okay, which is what it is. It's a mathematical model. You don't have a physical model. This is a mathematical model. So mathematically, when you break up your segments, they don't work. It doesn't work out. Now you're going to say, well, now this is where you can't bring in the physical, because this is not a physical model. It's a mathematical model. So in order to make the distance of drop, or whatever your drop, you call whatever the hell you want. It doesn't matter. It's uniform between these two. Okay, so whatever your x is, your z in 5 miles, whatever your z is in 5 miles, has to add up to your z's over the course of 1 mile, but they don't.
This is Houston. Say again, please.
Houston, we have a problem.
Okay, because it's just different. Because you're not measuring a physical object. If you were measuring a physical object, your sectional pieces would add up, but you're not measuring a physical object. One, you're measuring visual, here. So this would be the physical object if it was a ball that you would measure, but you're not measuring that, okay? What are you measuring? This area, the area of space above it, right? That's your drop. So you don't actually have the physical, you're not doing anything physical, because if it was physical, these would add up, and they don't.
But they don't add up that way, and this is why. You're moving the tangent line. When Cletus is standing at point 0, he's standing on this tangent line. But now, if we move to point 1, Cletus would be standing on this tangent line. And at point 2, he's standing on this one. And point 3 on this one, and so forth. That's where you're making the mistake. Cletus sees 8 inches at a distance of 1 mile. But at a distance of 2 miles, the drop becomes 32 inches from that same tangent line, and 72 inches at mile 3, and 128 inches at mile 4, and 200 inches at mile 5, using the approximate formula of 8 inches per mile squared. You can't move the tangent lines. You've got to work off of one. This one. That is the tangent line you've got to use.
So your numbers for how you mathematically model this aren't accurate. They don't work. So you need a new model. Literally. No, you literally need a new model. So you have to change your long ting, right? Your long curve needs to equal this. So now, because that mathematically, you have to plot this line, not this area of space. So when you plot this line, data, I'm just talking the data, right? We're not talking the shape of the earth, we're talking the data. And when we plot the Z, the drop, the value M, whatever you want to call it, the data. When we plot it 1 by 1 and in 5, it doesn't add up. So physically, it can't be what it says it is. Now, I know what you'll say, of course, but this is the numbers. I'm just working.
Hey, thanks for watching. Hope you guys enjoyed it. Don't forget to hit the like and subscribe buttons down there. Click that little bell if you want notifications. And shout out to all the great people who have supported the channel and supported the Cavendish experiment. We really appreciate it. And with that, I guess we'll catch you guys on the next one. Hey Gladys, we're out of here.